everyone. It's such a pleasure to be here. I'm standing underneath this incredible sculpture with all of you, which I'll try to illuminate a little bit today. This sculpture is by the artist Janet Echelman in her studio, Studio Echelman, and my research group and I had the great pleasure of collaborating with her on the software tools and mechanics behind the sculpture that I'll talk a little bit about. I also want to put this into a greater context, so I want to start with a little bit of history of my world of architecture and structural engineering. This is a long history that spans thousands of years, but things changed very dramatically in the last hundreds of years, where all of a sudden we had the invention of high-strength materials, structural steel, reinforced concrete, and high-powered computing, the ability to analyze structures with computers and represent them and draw them with CAD tools, which soon found their way into commercial software programs and then led the way to a new explosion of design, new types of forms that could basically do anything. So we're in this era currently in construction, which is pretty incredible. We can do absolutely anything we want. We have the high-strength materials. We have the simulation tools. There's sort of nothing that's impossible formally. But I think that brings a real challenge to us in this discipline, where these 19th century questions of what is possible to build and how can we possibly build it have really moved on to the key questions of what should we build and how should we build it. And this is really central to what this sculpture is about, which is the climate crisis. 40% of global greenhouse gas emissions are due to the built environment. A large percentage of that are due to the materials and the emissions associated with them, with the embodied carbon. And this varies dramatically across examples in the built environment. For example, the Beijing Olympic Stadium on the left has 14 times the embodied carbon per seat in the stadium compared to the London Olympic Stadium. They're both made out of the same material, steel. You've probably heard a lot about decarbonizing steel, which is absolutely important. But another key lever that we can address the climate crisis with is just using a lot less. Material efficiency is one of the major levers that we can do today to lead to better outcomes and also expand the design kind of palette of our built environment. This is not only this one example of these two stadia that have this incredible 14x differential. This is true across large samples of buildings that we're increasingly learning about through sophisticated data collection campaigns. This is from last year, where we looked at buildings over 300 or 400 buildings across the US. We see an 8x difference, again, in this key metric of how much carbon is emitted per functional unit, in this case, per floor area. We know how to use material efficiently. We've known from nature, from history, from structural mechanics. There are ways to wield material so that it can be used to its best capability, so it's maximally utilized. Things like following the beautiful lines of principal stresses in the veins of leaves, or shaping elements to remove material where it's unnecessary. These ideas go back hundreds of years, and yet they're relatively rare today. I'm part of this movement that these wonderful architects and engineers that I admire so much are trying to move past this, to understand material not only as something that enables us, but that can really form and shape our built environment in order for us to use it very minimally. So I love this quote from Eladio Dieste: "The resistant virtues of the structures that we seek depend on their form. It's through the structure's form that they are stable, not because of an awkward accumulation of material." And unfortunately today, most of what we see is indeed an awkward accumulation of material. And so this sculpture represents both the climate crisis, and I'll talk more about that in a moment, but also a new way to think about how we can use material in much more efficient and lightweight manners. It's really challenging to design in this way, to use material as it wants to be, because we can't impose the form on these types of systems. Typically, an architect draws a line, and that becomes a structure. It needs to be analyzed, like I'm showing in this animation, and then material is assigned to it based on the internal forces and stresses. If instead we let the form be what it wants to be, where it collapses into this state of pure tension, we gain huge efficiencies, but we lose control. Designers no longer get to impose the form. They need to find it and accept it and collaborate with physics to discover it. In my group, we advance computational tools to do just that, to allow designers and architects and artists to collaborate with the forces of physics. But this is not straightforward. For several decades now, architects have been fascinated with these really efficient forms, and yet they are also constrained by what's possible. There's this infinite spectrum of possible high-performing shapes. This is from Heinz Eisler, and yet not every shape that you can imagine is high-performing. So how do we navigate this paradox? The mechanics here say in order for material to be highly utilized, you need to use the full cross-section of it. So an element in tension is equally utilized. A shell that is acting as a membrane, all of the parts are used equally. Most structures in the world have the opposite. They have very little utilization and variation across the cross-section. How do we find shapes that have these magical utilization properties? This goes back to Robert Hooke, most famous for his third law of springs, but his second law introduced this idea of hanging a shape in tension and using that to find a form that works in pure compression. Tension and compression, the opposite forces. Antoni Gaudí used this idea to design the Sagrada Familia in Barcelona with a network of hanging chains to find these shapes, but he had to accept what the chains told him. He couldn't just impose his will. Frei Otto, the engineer in the 1960s, who advanced this with physical models that led to the amazing Munich Olympic Stadium in the 1970s, which also led to the development of computational tools to speed up this process. It's really hard to work with physical models because you can't iterate. Each step takes a huge amount of time and effort. In the computer, we could suddenly represent these systems, these equilibrium systems, rapidly, and yet they were still hard to work with for a long time because they were a one-way system. You had to tell the system what these kind of abstract parameters were and accept the output. In my research group, we've been advancing these tools in new ways for the last 5 years or so, inspired by Janet and in collaboration with Janet's studio, where we used recent advances like automatic differentiation, which helps us find how these simulation tools should adapt to a desired form. So for example, a shape like this is a prototype of this tool. If I change one of the elements, how do I find the structure that is as close to my goal as possible, but respects physics and equilibrium? Janet and I and a larger team have been kind of collaborating on these questions of tools and simulation for quite a while, for 10 years. This is a studio we taught together at MIT in 2017, where we explored and built forms, kind of exploring this idea of softness and how we soften ourselves in the design process. How can we be open to what physics wants to do? We taught a workshop a few years ago here at MIT while she was the CAST Distinguished Visiting Artist, where we kind of applied our tools with students to develop in one afternoon structures that work in pure tension and are incredibly lightweight. We fabricated them using the same techniques used to build this sculpture here through traditional rope splicing, a maritime technique. And then we developed sort of in concert this tool that led to this piece, which represents the Earth's climate history. This is the past, this is the future, and that moment of tension right here is where we sit today. And it's inspired by work from MIT climate scientists who've shown that we have many possible futures. We have agency in this world and we can act, and that will affect what happens. We don't have to accept the doom and gloom, but we do have to act. And so that's what this future portion represents here. We're in this moment of tension and we have agency and we need to act. To design this sculpture to represent this climate history, our process turned into this tool called Ariadne and Theseus, which you see here, developed by Adam Burke, which allows the designers to collaborate with physics to find a form that works in pure tension, but also visually represents the gesture, leading to this piece that you see here. Please also come back at night. It's absolutely incredible when it's illuminated, whose complex form was never possible before in Janet's work, before working with these new tools. We also developed a digital twin interface where you can play with the tool yourself, probably not while people are speaking, but during a break, I invite you to come to this kiosk here and try out the tool where you can see a version of the tool that we used in the sculpture, and also design your own tensile sculpture where you can play with physics and agency that you have as a designer to try to match a tensile system to a desired form, which we're seeing here. Finally, I want to speak a little bit to how this has catalyzed future research and invention. By developing this very specific tool for Janet and her studio, it has also inspired us to think of other ways that we can bring lightness into our work. And a lot of my other research is about reinforced concrete, the most ubiquitous material on Earth. 8% of global greenhouse gas emissions are due to cement alone. Of course, we need to find alternatives to cement, but again, we can also use a lot less of it through more intelligent design and shaping. One of the challenges is that it's very hard to construct irregular concrete forms, both because of their formwork and their internal steel rebar. Rebar is rigid and hard to work with, but what if instead we imagined tensile reinforcement systems inspired by these tensile networks that could be flexible and fine-tuned and customized and fabricated easily to the complex flow of forces and really align capacity and demand? We're experimenting with that now, again, with Adam, the student behind this work. Here's a prototype that we built with ice simulating concrete this winter, another brittle material that can't work on its own, but through a lightweight and intelligent distribution of tensile material can suddenly become very strong. To conclude, I'm really excited about the possibility to use softness, both materially and in our attitudes towards the world, towards design, and towards collaboration to change our future. Thank you.